Oops, my first video quit on me there, so picking up where we left off. If this is an exponential function, then when we plug in this next point, I'm going to plug in 3, we should get 42.9. So that's our test here. I'm going to plug in 3 for x, so I'm going to do 104 point, it's technically about closer to 918, times 0.7625 cubed, which we'll need to do in the calculator. So there's 0.7625. We're going to cube that and multiply. I think using the rounded number here is not going to be an issue. Clearly it's pretty far off. It's not 42.9. We get 46.512. And so this is definitely not an exponential model, although it's close. It's just not quite. Okay. Okay. Oops. Sometimes that happens here. See if I can fix that. Okay. All right. Moving on. Our next topic is, there we go, continuous exponential growth and decay models. So the difference between these and the models that I was looking at just in the previous video is that when you're talking about continuous growth, you're talking about something that grows very slowly, a little bit every little second. It's constantly growing or constantly decaying just by a little bit at a time, or maybe by a lot at a time, but the point is it's continuously changing, as opposed to maybe something like this where it says a population of 20 rabbits quadruples in size every 2 years, or maybe even the dog example is good too. So basically what this is implying, although it kind of implies that the population slowly grows, but really mathematically what is happening here is that you have 20 rabbits and then you stay at 20 rabbits and you stay at 20 rabbits until, well, not exactly, but until 2 years later when it quadruples and you have 40. Now that's not exactly true because you can plug in different values of t and you would see that it does actually for various values of t increase a little bit constantly. But what is different is there's a slight difference in the growth rate really, and that models of this form you might like multiply at the end of 1. So maybe your t or your x has to be an integer. So when t is 0, you have 20. When t is 1, you've got 40. When t is 2, you've got 80. Whereas with exponential continuous growth and decay models, it's constantly changing. Okay, so both forms, whether you're growing or decaying, take on the same form, y equals a times, now you can use any base, but the common base to use is e, Euler's number, 2.71828, so on. So e to the rt. This is the most common form. A is your initial value, just like with the other ones with c. R is the growth rate per unit time, and you can write that as a percentage or as a decimal. T is time, and then the other thing here is if r is positive, you're going to have a positive exponent, so you're going to actually have growth, or if r is negative, you would have a negative exponent, which means similar to this one back at the very beginning, like this, where we had the negative exponent, that means you're having decay, so a decreasing exponential function. Okay, so let's look at an example here. A colony of bacteria with unlimited resources grows exponentially according to this function, where n is measured in grams and t is measured in days. Okay, so the initial amount of bacteria, that's when t is 0. So n of 0 would be equal to 500 times e to the 0.065 times 0, so e to the 0, which is 1, so 500. Okay, which you probably could have gotten just from looking at the 500 right there, which is the coefficient of e. And we are in grams here, so 500 grams. Now it says, what is the growth rate? The growth rate is it's right here, it's the continuous growth or decay rate. That's R. Okay, in this case, R is equal to 0.065, but typically if you're asked what is a growth rate, you would probably answer as a percentage. So moving this decimal over, this means 6.5% per, we are in days, 6.5% per day. That's how much it's increasing by every day. Okay, so what is the population after 5 days? Well, that would just be to plug in 5, take n of 5, we get 500 times e to the 0.065 times 5, which we need a calculator for. So 0.065 times 5 in our exponent. That's the exponent on e, so e to the 0.325 would be e, hold on, there we go, I hit the wrong button. So 0.065 times 5 is 0.325. Then we're going to hit the e to the x button. There we go. So e to the 0.325 would be 1.384. Now I'm going to multiply that times 500. And we get 692.015. And you want to ask, is that a reasonable answer? Well, if you start with 500 grams and you increase it about 6.5% per day, it seems like after 5 days, having 692 is pretty reasonable. Okay, and how long will it take for the population to reach 800 grams? Okay, so this involves a little bit more. We're asking how long will it take, so what's the time? You want t when n, the amount n, is equal to 800. So here we're going to plug in 800 for n of t and then solve for t. So we get 800 equals 500 times e to the 0.065 t. And we need to solve this exponential equation for t. So the first thing we're going to do is get the 500 out of the way before taking any logs or anything. So we're going to divide 800 by 500, which is 8/5, equals e to the 0.065 t. Now to get that variable out of the exponent, you can either rewrite this in exponential form or you can take the log of both sides. And anytime you're dealing with e's, I would use natural log. So I'm going to take the natural log of 8/5 is equal to the natural log of e to the 0.065 t. And the natural log and the e cancel here on the right. So we have natural log of 8/5 equals 0.065 t. And so t, as an exact answer, equals the natural log of 8/5 divided by 0.065. Of course, that doesn't really make sense. Now, on your final exam, where you don't have a calculator, that's what you would write. But if this is an applied problem, so we are going to approximate. So 8/5 is that. We take the natural log and divide by 0.065. And we get 7.23. So after about 7.23 days, the population would be 800. All right, let's do another example. So a car was valued at $38,000 in the year 2007. By 2013, the value had depreciated to $11,000. And if the car's value continues to drop by the same percentage, what will it be worth in 2017? All right. So we are dealing with a decay model here because the car's value is decreasing. But you work the problem the exact same way and the numbers will just naturally work out that way. So the model is y equals a times e to the rt. Okay, now we don't have the model, but that is the model. So in order to find this model, we're going to need to find both a and the rate r. E is the number 2.718, t is your variable time. So we need a and r, and we're going to have that model in order to figure out what it's worth 10 years after the initial time. Now you could actually use t equals 2007 and t equals 2013 or 2017, but that's some pretty large values for t. Now it'll work if you do it, it's fine, but instead what I'm going to do is let's let t equals 0 correspond to the year 2007. That's when we're starting the value. So when t is 10, that would be 2017 and so on. Okay. If we do it that way, it makes it a little easier also because then the initial value a occurs when t is 0. So we automatically know that a is 38,000. And all we have to do is find r. So in order to find r, we're going to have to use the fact that in 2013 the value was 11,000. So y is 11,000 when t is, let's see, that's 6 years later, so when t is 6. And we can solve that equation right there for r. Okay, so same as before. First we divide by 38,000. So we'll get 11 over 38 when we do that, equals e to the 6r. Then we can take the natural log of both sides. So the natural log of 11 over 38 equals, when I take the natural log of e to the 6r, it's going to simplify to 6r. So the exact value for r is the natural log of 11 over 38, and that is divided by 6. Which on an exam without a calculator you would just answer like that, but let's go ahead and get the decimal value for r here. And minor rounding errors can cause major errors in exponential functions because it's like that error is multiplied essentially. Alright, so there's 11 over 38, and I'm going to take the natural log and then we're going to divide by 6. Okay, so what I was saying there is we want to carry this out to a whole lot of decimals, because if I was just to round and call it negative 0.21, my answer might be way off later on in the problem. So I would carry this out, you know, as many decimals as your calculator has. That's a bit excessive. But I'm going to go with negative 0.206615. 0.206615 for r, which is negative, which worked out naturally, so that means it's a decay problem. So then our model is y equals 38,000 times e to the rt, so negative 0.206615 times t. Okay, there's our model. Let's box that since it's important. Okay, now it says if the car's value continues to drop by the same percentage, what will it be worth in 2017? So that's 10 years after 2007, so we would plug in 10 for t to get, let's see what that comes to. So we have this number, which since I didn't clear the calculator, I can just reuse it and say times 10. Now I'm going to raise that as an exponent on e and hit times 38,000. I find that quite amazing that that worked out so nicely. That is not correct right there. Let's try that again. Okay. Okay, I don't know what's wrong with this calculator. Maybe I'm using it wrong, but when I do this on a handheld calculator, it comes out correctly. So when we compute this number right here, and then I multiply by 38,000, I get 4,813.56 when I round. So that would be the value after 10 years, which sounds reasonable for an answer for that exponential decay model.